So we want to learn about this perfect graph. We define this perfect graph to be the graph whose induced subgraph or induced subgraph satisfy this min-max relationship between chromatic number and Killing number. Okay, and we want to first consider some examples of this perfect graph. And for that, we want to define this concept. We say a graph is a whole or orderly cycle in a graph G is a cycle of length at least 4 having no chords. So in other words, it is the induced cycle, induced subgraph that is a cycle of length at least 4. So we say that's whole or chordally cycle. And we say a graph is chordal say a chordal graph if it has no chords. So if a graph has no chords at all, then we say that this is a chordal graph. And there is one good way to understand the structure of chordal graph. And in order to explain that, we define this concept. A vertex is called to be simplicial if its neighborhood induces a clique. A vertex is there, and then if you take its neighborhood, and then in this neighborhood, everybody is adjacent, and you say that this vertex is simplicial vertex. And we say a simplicial or perfect elimination ordering is an ordering Pn to P1. So index is going from up to downward, in which the vertices can be deleted so that its vertex Pi is a simplicial vertex of the graph induced by the vertex P1 to Pi. So how do you do it? You take a graph and then you take a simplicial vertex and then you delete. And you take the simplicial vertex and you delete. You simplicial vertex and you delete. And these are the order of deleting. This was the one that's deleted first, and the second and third. So that's simplicial elimination order. And this concept of simplicial elimination ordering give us an understanding on this chordal graph because of the following theorem. A graph G is chordal if and only if it has a simplicial elimination ordering. So if your graph is chordal, then you can find the simplicial elimination ordering. And if you can find the simplicial elimination ordering on the graph, then your graph must be chordal. Okay. Let's prove this direction first. So take the contrapositive. If your graph is not codal, if G has a coordinate cycle, so or C, then what? Some vertex in this C must be deleted. And we take the first vertex in any ordering, in simplistic elimination ordering. First vertex deleted from this C in an elimination ordering. So once you are deleting this, it may have other neighbors as well. But one thing we know is that these two are not adjacent. Because this is a hole, that means there are no chord. So this first vertex has two non-adjacent remaining vertices. Non-adjacent remaining neighbors. Hence, such a graph has no simplicial elimination ordering. Okay. So let's prove the other direction. If it is codal, it has simplicial elimination ordering. One thing we know is that the codal graphs are the graphs with no chord. So if you take an inverse subgraph of codal graph, then that's also codal. Because, I mean, your inverse subgraph also cannot have an inverse subgraph which is a chord. So the family of codal graph are hereditary. What does it mean? It implies that it suffices to prove that every codal graph has a simplicial vertex. So if your graph has a simplicial vertex, if your graph is codal, you find one simplicial vertex and then you delete. Then remaining graph is also codal. So because of what you prove, it has a simplicial vertex, you delete. Then remaining one is also codal, you take one vertex, one vertex, one vertex, this gives you a simplicial elimination ordering. So we want to prove this. We use induction to prove the following strong statement. So this stronger statement facilitates the induction. Sometimes when you want to prove something using induction and it's not working, then you make the statement stronger. So your induction hypothesis gets stronger, so it might help you. If a codal graph is not complete, not a complete graph, then it has two non-adjacent simplicial vertex. So we will prove that it not only have one simplicial vertex, it has two non-adjacent ones, as long as the codal graph is not a complete graph. Okay, let's say you have a codal graph G. If this is complete graph, then there is nothing to prove. So otherwise, let X and Y be non-adjacent vertices in G. Okay, you have X you have y. As they are non-adjacent, you can find the separating set that S, the minimal set of vertices whose relation separates x and y. Because they are not adjacent, such a thing exists. I mean, for worst case, you delete everything except x and y. Then, I mean, it's separated. So among them, you choose a minimal one. So we first claim that the S is a clique. Why? I mean, if you have a S, I mean, if S is just one vertex, then that's a clique itself, K1. So you're okay. If there are two vertex, at least two vertex, say U and V, you choose arbitrary one. Then what happens? You have some component, say A and B, which contains X, which contains Y. So once you delete S, then you have this component and this component. And because S is the minimal separating set, U sends an edge and B sends an edge, U sends an edge, B sends an edge. It could be same or not. I mean, it sends an edge and it sends an edge. So let U be the distinct vertices in F. And by the minimality of F, both U, V have labels in A and B, where A, B are the components C minus F containing X and Y respectively. Okay, then what do we do? Then you take you take this graph and then take the shortest path between U and B through A. You take this, you take the shortest path between these two. So, okay, what I mean is that, okay, let me restate. So we don't care whether there is an edge between or not. So we will show that there is an edge, but for now, we don't care. We just take A, and then U has at least one neighbor, B has at least one neighbor. So inside of A, you find the shortest path between this vertex and this vertex. If these two happen to be the same vertex, then yeah, this is already, what we want, the shortest path. If those two are different, then you find the shortest path. So you do the same thing here, and then you take the union. So the union of shortest UV path through A and B. You take this and you take this, then this is the length at least 2, this is length at least 2. So it could be longer, but its union is a cycle of length at least 4. And by the choice, we choose the shortest one. So choice of the paths, and because there are no edges between A and B, once we have such a cycle, then between these vertices, there are no edges. There are no edges. If we have an edge here, then we take a shorter one, right? Because this is shortest. There are no edges between here or here. and there are no edges between here or here or here, and there are also no edges between here and here because there are no edges between A and B. So the only possible chord is that this cycle has no chord other than UB. The only possible chord is it. And since UB in X were arbitrary vertices, we consider that F is a clique. We conclude that the S is a clique. Okay, this shows this claim. Now what? Now you have F, which is a clique. You have this A, and then you have this B, containing X, containing Y. And let G1 be the induced subgraph of G, consists of A and F, and G2 be the one consists of the B and F. And each of these is a Koldal graph because they are induced subgraph of G. And what? If one of them is complete, then we know that any vertex in it outside S is simplicial. If this one is perfect, then this vertex is simplicial because it's also here. This may not because this might have labels here, and then these are non-admitted. But as long as you choose it from here, this is simplicial. Otherwise, if this is not complete, then what happens? You can apply the induction hypothesis. Gi has two non-adjacent simplicial vertices. By the induction hypothesis. And what do we know? Since this F is a clique, at least one of these two non-adjacent simplicial vertex is outside F. So that shows that there is simplicial vertex here and the simplicial vertex here. No matter whether this is complete or not, this is complete or not, you can find one simplicial vertex here, one simplicial vertex here. Moreover, they are not adjacent because a vertex in Gi outside of S has no neighbors in G outside PGI. Thus, we find two non-adjacent vertices which are simplicial. This proves what we want. So these Koldal graphs are the ones, exactly the ones that having simplicial elimination ordering. And once we have this simplicial elimination ordering, you reverse it. Then it's not, so elimination ordering is one by one, you delete it, right? If you reverse it, it's more of a construction ordering. You add one vertex, you add one vertex. That gives you the entire graph, right? So it shows that every Koldal graph is obtained from K1 by iteratively adding a new vertex with neighborhood. Is a click. Okay. Using this construction ordering, we can prove what we want. The causal graphs are perfect. Why? Simply what we do is you take this reverse of simplicity elimination ordering. Then you get this V1, V2, Vn. And you run greedy coloring algorithm with respect to this ordering. Then what happens? This gives you a coloring, proper coloring with say K color. Assume this gives you a K color. That means there is some vertex which is colored by K. But what does it mean? It means that at this point, it has neighbors which contains colors from 1 to K, minus 1, right? But what do we know? In this ordering, this neighborhood is a clique because you are dealing with causal graph, which has a simplicity elimination ordering. So this is the reverse of simplicity elimination ordering. So at that point, this is a clique. So if it uses K color, that means there is a clique of size K. So this clique of size K minus 1 together with this vertex give you a clique of size K. So chromatic number being K here implies that the omega is at least K, but we know that the clique chromatic number is also upper bound. So for this simplicial elimination ordering give you the fact that the chromatic number and clique number are same for this causal. So I will not write down the proof, but this shows that the causal graphs are perfect. Okay, so that gave us some examples of perfect graph. And there are more examples of perfect graph. And we can prove that the following factors of graph are perfect. So first, we can check that the bipartite graph are perfect. Why? Bipartite graph, I mean, the chromatic number of bipartite graph is 2, and bipartite graph does not contain triangle, so its ring number is also 2. So it's same. So this is perfect. Okay, and also we know that the line graph of bipartite graph are perfect. Why? If you have a line graph of bipartite graph, then what's the chromatic number of line graph of bipartite graph? This is same as the chromatic index of graph, H chromatic number. And we know that this is same as the delta of G. So previously we proved this Koenig theorem that for bipartite graph, these two are equally. Bipartite graphs are class 1. On the other hand, what's the clique number of line graph of G? So cliques in line graph are exactly one of the following. It's either a star at one vertex or a triangle. This could happen. I mean, this is not star, but all 3 of them are adjacent. all three edges are adjacent in the line graph. But this doesn't happen in bipartite graph. In bigraph, this does not occur. So that means this equality also holds. So line graphs of bipartite graphs are, perfect. Then the complements of this line graph or bipartite graph are also perfect. Why? So if you have a independent set in the line graph, it is same as the matching in G. And clique of LG is again this star or triangle. Then, as we mentioned, this doesn't appear. But what do we know? The Koenig-Edgerbury theorem says that the clique number and vertex cover number is same. And this is alpha of L of G. And what's this clique cover number? I mean, this vertex cover number. Vertex cover number is that you find the vertex so that all the edges are adjacent to one of them. And that's same as taking these vertices, then you take the stars around it. And that covers all the edges, right? And these edges are the vertices in L of G. And each set of edges incident with a vertex in this vertex cover corresponds to clique. So this is same as the clique covering number of the line graph. So this is what? This is same as the chromatic number of complements of the line graph. And this is what? This is the clique number of complements of the line graph. So this shows that the complements of line graph of bipartite graphs are perfect. And also, complements of bipartite graph are perfect. So before we prove this alpha of G is same as beta prime of G. And what's this beta prime? This is edge covering number. Edge cover. And what's this edge cover? In bipartite graph, cliques are all edges. There are no larger size cliques. The edge cover is same as the clique cover. So this is same as the clique cover number of G. And alpha of G and clique cover number are same. That means this is what? Omega of G complement. And then this is chi of G complement. So they are same. So this is also perfect. So this give us some classes of graphs that are perfect. Okay, and if you see here, there are some patterns. These two are complement each other, and these two are complement each other. So, based on this pattern, there is this conjecture by Birds, which is called perfect graph conjecture, and now it's called perfect graph theorem, which said that a graph G is perfect if and only if its complement is perfect. So this was conjecture by Barrett. And in 1972, Robert proved it. And she was actually, I mean, she's relevant. He was 22 years old when he proved it. Okay, and yeah, I want to discuss about the proof of this perfect graph theorem. So I will present you a proof which is not discovered by the robot. There is the shorter proof discovered later, and I want to talk about that. And yeah, maybe because I don't want to make this video to be too long, so let me break it here, and then I will prove this theorem in the next video.